You know that feeling when you hear about all the incredible advancements happening, AI, biotech, space exploration, and then you kind of wonder, are we really preparing the next generation for all that?
Yeah.
So many of us worry our kids are just, well, memorizing facts, not learning to think or to solve the really complex problems coming down the line. Today, we're doing a deep dive into an educational approach that could fundamentally change that. Powering up STEM implementation in education. We're going to unpack what a true STEM approach actually means and, how we can foster that deeper learning and those problem-solving skills students genuinely need for an uncertain future. For this deep dive, we've looked at a great collection of articles from Creative Educator and also a really insightful YouTube video from Melinda Kolk. They both shed light on integrating STEM with project-based learning.
Yeah, and our mission today is to really get under the hood of how educators can use a holistic STEM approach. Guide students through these design processes, scaffold their problem solving effectively, and really embrace project-based learning to build those critical skills. Skills for a world that's changing incredibly fast.
Okay, let's unpack this then, because in a world changing so quickly, how do we equip learners not just with facts, but with the ability to solve these complex, interconnected problems of tomorrow? So let's start with the definition. When most people hear STEM, they usually think, okay, more science, tech, engineering, math, maybe separate classes, more focus there. But the sources suggest it's much more than that, right?
Absolutely. That's a really common starting point, but it kind of misses the core idea. STEM is way more, as one source puts it, than just adding focus. It's fundamentally about teaching these subjects through an integrated approach. Think about it, real-world problems rarely fit neatly into just one box. An engineer doesn't just do math detached from everything else. They apply science. They use tech. So this approach deliberately blurs those traditional lines between subjects. It reflects how real work actually happens.
Right.
The heart of it is focusing student work on ideas, questions, problems that require thinking across disciplines, connecting the dots.
So it's this holistic approach to curriculum then. What does that practically mean for a student? How does seeing those connections, thinking deeper than just facts, actually benefit them?
Well, the fascinating thing is how directly this builds those essential skills.
Hmm.
People often talk about the 4 Cs, right? Creativity, collaboration, communication, critical thinking. This integrated way of working, this cross-disciplinary thinking, it nurtures exactly those skills. One source flat out says this approach is necessary for success and innovation today. Because think about the big challenges, climate change, health breakthroughs. They demand people who can pull knowledge from different fields and work together, flexible thinkers.
That makes perfect sense. So the idea is this better prepares them for those complex problems, makes them more career ready and globally competitive. It's about applying knowledge in new ways, not just knowing stuff.
Exactly. And some even push it a bit further, integrating the arts, turning STEM into STEAM.
A STEAM, right.
Yeah, that allows students even more ways to express their understanding, maybe through song lyrics about a science concept or, creating multimedia projects. It adds another layer.
This integrated thinking sounds powerful, but okay, here's where it gets really practical, I think. How do educators actually guide students through this? Through solving complex, sometimes messy, real-world problems? Is there a framework?
That's a key question, because without some structure, it could just feel chaotic, couldn't it?
Yeah, absolutely.
So most STEM educators do use a structure. Often it's something like the engineering design process. And the Museum of Science in Boston has a well-known one, or design thinking, which might use phases like frame, imagine, make. But the important thing is these aren't rigid step-by-step recipes. They're described as inquiry-based processes. They provide structure, yes, but for learning and action. They're usually circular or cyclical and iterative.
You can loop back.
Exactly. You might get to the create phase and realize you need to go back and ask more questions or imagine different solutions. It's fluid. Should we break down those phases a bit?
Yeah.
And the tools?
Yeah, let's do that. How do you scaffold the thinking?
Okay, so first up is usually the ask phase. The whole point here is identifying the problem clearly. Using observation, discussion, asking good questions. Who actually has this problem? What exactly is it? What solutions have already been tried? For scaffolding, you could use something like a Think Puzzle Explore organizer. It helps students tap into prior knowledge, sparks curiosity, gets them ready for inquiry.
Okay.
But maybe even more critical is an empathy map. This really helps students focus on the audience for their solution, define their specific needs, figure out the must-haves.
Can you give an example of that?
Sure, like if students are designing a better school locker system, the empathy map gets them thinking beyond just storage. How does the student feel when they can't find their books? What are their daily frustrations? It humanizes the problem.
Ah, right. Makes it real.
Yeah,
Yeah.
and the ideal scenario is always a real problem for a real person or community. To dig deeper into why the problem exists, the 5 whys method is great. Sakichi Toyota at Toyota developed it. You literally just keep asking why,
Yeah.
like a persistent kid.
Huh. I can picture that. Okay, so it's not just jumping to solutions, but really digging into the problem
You're
first.
Precisely. That deep understanding is crucial. Then you move into the imagine phase, brainstorming time. And the key mantra here, according to the sources, is volume of ideas, not the quality of them, at least initially.
Get everything out there, good or bad.
Exactly. Our brains tend to self-edit too quickly. We want lots of options first. Maybe use cluster diagrams or just plain old brainstorming to generate loads of ideas, even the wild ones.
Okay.
Then, once you have a bunch, you need to narrow it down. A tool like Edward de Bono's Plus Minus Interesting, or PMI organizer, is helpful here. Look at the pros, the cons, and just the interesting aspects of each idea to help decide.
Interesting. Not just good or bad.
Right. Sometimes an idea isn't clearly good or bad, but it has interesting potential or raises new questions. And if students get stuck, de Bono's 6 thinking hats can help them approach the problem from different angles: logical, emotional, creative, etc.
Got it. So ask, then imagine. What's next?
Next up is the plan phase. Now you've got an idea, maybe refined it a bit. This phase is about choosing a direction and making a concrete plan. It's really about project management skills. How do we make this idea real?
Right, the logistics.
Yeah. Tools here could be a cycle organizer, which is kind of like a storyboard. It helps break down big processes and reinforces that cyclical nature we talked about.
Yeah.
Or maybe a more linear sequence chart or a flow chart to map out the specific actions needed.
Okay, this is where the idea starts to take shape, feels more achievable, but then comes the actual doing, right? The create phase. I bet that's challenging.
It definitely can be. That's the create phase.
Yeah.
Students design, build, code, whatever the solution requires. And this is where, misconceptions often really surface.
Okay.
It can be tough to manage because different students or teams might be working at very different paces, hitting different roadblocks. So the key here is regular check-ins, both quick verbal ones and maybe written reflection.
Like exit slips.
Yeah, exactly. Like a 3-2-1 exit slip. What 3 things did you discover? What 2 things were frustrating? What's 1 thing you need to do tomorrow? Things like that. And just talking face-to-face is vital to catch misunderstandings quickly. And for ongoing reflection, process journals or logs are fantastic. Students can jot down notes daily about their effort, their progress, what they learned. Remember that John Dewey quote, "We don't learn from experience, we learn from reflecting on experience."
That's powerful. So the journal helps make the learning stick.
Definitely. And finally, after creating something, you hit the improve phase. This is critical. Did the solution actually solve the original problem? And how can it be made better? Engineers, designers, they iterate constantly. The first version is just that, a first attempt. So tools like rubrics and checklists help students evaluate their own work against the criteria. Where did it succeed? Where does it need work?
And feedback from others.
Hugely important. Formalized peer feedback is great. Using structures like warm and cool feedback, something positive, something constructive, or sentence starters like, "You did a great job of," or "Have you considered?" It builds a growth mindset, helps them see feedback as useful, not just criticism.
What strikes me through all this is the educator's role. It's not just teaching content, it's guiding, facilitating, scaffolding. And the stories mentioned providing a decreasing number of scaffolds over time.
That's the goal, absolutely. As students build these skills, problem solving, planning, evaluating a few, you gradually provide less detailed support. Maybe initially you give them the rubric, but later they help create the criteria for success. You're transferring that responsibility.
That's real empowerment. Okay, so we've got this holistic STEM idea, we've got the design process guiding it. How does project-based learning, PBL, fit in? How does it, as you said, supercharge this?
PBL. Yeah, it can take this whole STEM implementation even further. It fundamentally flips the usual classroom model.
Flips it how?
Instead of learning content and maybe doing a project, with PBL, students are presented first with a genuine problem or issue, often something right in their own community. Then, they learn the content, the science, the math, the history, whatever's needed, specifically because they need it to answer the questions they develop while tackling that problem.
So the problem drives the learning.
Precisely. Students aren't just doing activities the teacher sets, they're crafting innovative solutions based on research, their own experience, their imagination. The sources emphasize that in PBL, questions are more important than answers.
Hmm.
Think about this example. Instead of the teacher saying, build a compost bin or calculate cafeteria waste, a PBL approach might just involve showing students the sheer amount of waste produced in the cafeteria one day. Full stop.
And then,
And then the students might set the goal. We need to reduce this waste. They figure out how to break down that big problem, research options, choose their approach. Maybe it's composting, maybe it's advocating for different food packaging, maybe something else entirely. The ownership is theirs.
I see. It starts with the real-world observation.
Exactly. Or think about a school garden. Lots of schools have them. But in a true PBL approach, the students drive it all. They decide the purpose is about healthy eating, sustainability, supporting local wildlife with native plants. They research what to plant, when, where. They manage the whole thing.
That really puts students in charge, as the source material says. They're doing real work, learning academic skills along the way.
Right. And there are some key reasons why PBL works so well for STEM goals. First, PBL helps students bridge thinking across disciplines. Real problems are messy, complex. They don't fit neatly into science or math. You need to draw on lots of different knowledge areas.
Like the real world.
Like the real world.
Yeah.
Second, PBL promotes deeper connections to content. Because it's inquiry-driven, focused on uncover, not just cover, students have time to really grapple with ideas, connect them, see what they know and what they still need to know. It's a genuine deep dive into the content that matters for their project.
Avoids that surface-level memorization.
Exactly. Third, PBL fosters crucial inquiry skills. Because the problems are open-ended, questions just lead to more questions. How do we make lunch healthier? Leads to questions about nutrition, student preferences, food waste, costs. It pushes beyond simple answers, demanding creative and analytical thought.
So it encourages curiosity.
Absolutely. And fourth, PBL fosters reflection and metacognition. That whole process is recursive, constantly asking, what do we know? What do we need to figure out? What worked? What didn't? Why? That reflective loop helps students connect the content to their own thinking, their problem-solving process. It helps them understand how they learn. Using those daily reflection journals we talked about, maybe digital ones like Wixie or Padlet, makes that learning visible.
It seems so clear then. If we really want students to take ownership of their learning, we have to empower them. Give them opportunities to do real, meaningful work at school that builds not just academic skills, but also the thinking habits, the dispositions they need to actually use their learning to solve problems and innovate.
That's the core message, I think. It's a shift in perspective.
So wrapping this up, our deep dive today really highlights that STEM education isn't just about focusing on 4 subjects in isolation. It's far bigger than that. It's about an integrated, holistic, active way of thinking and problem solving.
Absolutely. And by using these iterative design processes, by really embracing project-based learning, educators can empower students. Empower them to ask meaningful questions, tackle complex issues head-on, and develop genuinely innovative solutions. That's how we prepare them for whatever the future holds.
So here's a final thought for you listening. Think about a challenge or a problem you're facing, maybe in your work, your life, or your community. How might applying that cyclical design process, ask, imagine, plan, create, improve, or even a full project-based approach fundamentally change how you tackle it? And maybe more importantly, what might you learn along the way?